Hi everyone, welcome to our lecture on Nyquist stability analysis. We will continue our discussion from last time, do another example using Nyquist stability analysis, and we'll look into some special cases. First, let's remember what Nyquist is. Nyquist is a tool for assessing the stability of a system when we have limited information about our transfer function. What we saw last time was that if I have a closed loop feedback system with feed-forward transfer function g of s, a feedback transfer function h of s, and let's say my input r of s and output y of s, I define loop gain L of s, which is going to be the multiplication of the feed-forward transfer function times the feedback transfer function. Then what I do is I move along the j omega axis from very large negative frequencies all the way to 0, all the way to very large positive frequencies. And for each particular frequency, I find L of j omega and plot it in a complex domain. So for each frequency here, I find what the magnitude and phase angle of L of j omega is, and I find the corresponding point here. Then by connecting these points together, what I will get is a closed loop graph or plot, which would be my Nyquist plot. We use this plot to assess the stability of the system, and if you remember, the equation that we use is z equals n plus p. P being the number of unstable poles in the loop gain in L of s, n being the number of times that the Nyquist plot will encircle -1 in clockwise direction, and when I add n and p together, z will be the number of unstable poles in the closed loop system, which is what I'm interested in. We did an example last time, but just to make sure that everything makes sense, let's do one more example. So this is the new system that I have. With a unity feedback and a feed-forward transfer function of the form s minus 10 divided by s minus 1 times s minus 2. So the system has 1, 0, and 2 poles, all of which are located in the right half plane. The first thing we do is we rewrite this system in the form of a standard format. So my L of s, which in this case would be s minus 10 divided by s minus 1 times s minus 2, I will basically take the constants out and I will say minus 10, and I will write this as s divided by minus 10 plus 1 divided by minus 1 s divided by minus 1 plus 1 times minus 2 s divided by minus 2 plus 1. And again, as you remember, this is the term that we care about, which is the low frequency term. In this particular case, it's going to be minus 5. Next thing I do is I form that table consisting of the break frequencies. So I will have all the break frequencies, what type they are, where they are located, and of course based on that I will look into the slope of magnitude and phase angle. So let's start in an ascending fashion. The frequencies that I have would be 1, 2, and 10. 1 is a pole, is a first order pole, so I would say times 1, and it would be in the right half plane. Because it's a pole in the right half plane, the slope of the magnitude is going to be minus 20 dB per decade, and the slope of phase angle is going to be plus 45 degree per decade. Remember that when you have a pole in the right half plane, the slope of the phase angle is going to be positive. For 2, we're going to have a similar fashion. So we have, again, a pole. sorry, this is a first order pole, so one pole, right half plane, minus 20 plus 45. 10 would be a 0, so that's a 0, and it's first order. It's in the right half plane. Because it's a 0, the magnitude is going to be positive. And you remember that the slope of magnitude for a 0 is plus 20 dB per decade, regardless of whether the 0 is in the left half plane or the right half plane. But because this is a 0 in the right half plane, the slope is going to be minus 45 degree per decade for phase. Okay, so let's now go ahead and plot the Bode plots for magnitude and for the phase angle. So let's say this is 1, and this is, let's say, 10, and this would be, for example, 2. Now my low frequency term is minus 5, so when I'm dealing with magnitude in decibels, which would be 20 log of G, I'm looking at 20 log of 5. Now 20 log of 5, what we know is that it's a positive value. So this would be, let me use a different color. Let's say this is 20 log of 5. So I would say this is 20 log of absolute value of minus 5, which is 20 log of 5. Then, when you get to 1, this is your first pole, so you're going to start with a negative 20 dB per decade. When you get to 2, that's going to be the second pole, so you add another negative 20 dB per decade. So let's say this becomes a little bit steeper. So this would be minus 20 dB per decade. This would be minus 40 dB per decade. And then when I get to 10, which will be a 0, it will add a positive 20 dB per decade. So I will go back to minus 20 dB per decade. This is going to be my magnitude Bode plot. We can do the same thing for the phase. Let me use a different color and perhaps try to be a little bit neater with my diagram. So my low frequency term is minus 5. That's a negative number, so the starting angle is going to be minus 180. And then what I have to do is I have to find the ranges for which I have a non-zero slope for my phase angle. So let's start with the first break frequency, which is 1. I know that I have a slope of plus 45 degree per decade between 0.1 times the break frequency and 10 times the break frequency. So let's say it would be from 0.1 to 10. This is going to be plus 45 degree per decade. The second break frequency is 2, so I will have a phase of plus 45 that goes from 0.2 to 20. So let's say 0.2 is somewhere here, and 20, let's say it's somewhere here. That's another 45. And then lastly, I have a 0 at 10 with a phase slope of minus 45. And the range for that is going to be 0.1 times 10 and 10 times 10. So let's say from 1, assuming 100 is going to be somewhere here, I will have a minus 45 degree per decade. So now what I'll do is I will start from here, assuming this is minus 180 degrees. Then I will have a slope of 45 degrees up to this point, and then I will have another 45 degree added to it. So this is going to be, let's say, 90 degree per decade. And then I will have a 45 here. So from here to here, it's going to be 45 plus 45 minus 45. So it's going to be 45. And then from here to here, it's going to be 45 minus 45. So that's kind of the 0. And then from here to here, it's going to be minus 45. So I will go somewhere here. And then after this, it's going to be a flat line. So this is going to be my phase plot. And let me go ahead and erase this axis because I'm not really sure where the 0 is going to lie. I really have to find all the breakpoints and calculate what the phase angles are. So 0 might be somewhere, for example, here. Anyway, so this is going to be my phase plot, and I can identify the phases as 45 degree per decade. This one is going to be 90 degree per decade. This is going to be 45 degree per decade, and this is going to be minus 45 degree per decade. This is my Bode plot for both magnitude and phase. Okay, now that we have the Bode plots, we can go ahead and draw the Nyquist plot using that. So what we'll do is we'll start moving from a small positive frequency to a very large positive frequency, because that's what Bode plot gives us. For each particular frequency, we find the magnitude and phase angle, then we plot those dots on the Nyquist plot, connect them together to identify what the plot of the Nyquist is going to look like. So this is what I have captured from your notes. These are the frequencies that have been essentially identified. So you can see that I start from about 0.1 radian per second and then go all the way to 100. And these are the corresponding magnitudes and phase angles. So let's go ahead and identify these points and then connect them together. Let me use a different color. So the first one is going to be 0.1 radian per second. Magnitude is going to be 5, and phase angle is minus 180. Minus 180 is somewhere here, and let's say this is 5. Then we have 5, again the same magnitude, with a slightly less negative angle. So minus 166, let's say it's going to be somewhere here, and I'm assuming this is still magnitude of 5. Then I will go to minus 103 with a magnitude of 5. So this is a 90, and then let's say minus 103 is going to be somewhere here. And then we have minus 90 with a magnitude of 2.5. So let's say I am somewhere here. Minus 58.5, which is going to be somewhere here with a magnitude of 0.1. And again, a minus 90 with a magnitude of 0.01. So somewhere here. So I will now connect these together, and I will put an arrow to identify the direction of rotation. Now, this of course corresponds to all the positive frequencies. As you know, for a proper function, the negative frequencies will have the same kind of pattern. It's just that it's going to be the flipped version of the positive frequency. So the negative frequencies will most likely have a shape like this. So this is going to be my Nyquist plot. Since this point has a magnitude of 5, or in fact it's a minus 5, minus 1 is going to be inside the Nyquist plot. So let's do the analysis now. Z is n plus p. Now if you remember, in the function we had 2 poles in the open loop gain. We had 2 poles in the right half plane. So P would be 2. In other words, my open loop system has 2 unstable poles. Now look at the Nyquist plot. It's actually encircling -1 one time, but it's doing that in the counterclockwise direction. Because it's counterclockwise, the sign is going to be negative. So z will be 2 minus 1, which is 1, meaning that the closed loop system is going to have one unstable pole, and for our purposes that means the system is unstable. Now there are certain types of functions that require special attention when we want to draw their Nyquist plot, and these are functions that have poles on the j omega axis. Let's remember what Nyquist does. We move along the j omega axis. For every frequency, we find what the open loop gain is at that particular frequency. So if I want to plot what we have seen before, is I will move from a large negative frequency to a large positive frequency. For each particular frequency, I find out what L of j omega is at that frequency. So what is its magnitude? What is its phase angle? This is going to be its magnitude. Erase that. So this is going to be the magnitude. This is going to be the phase angle. Then I do this for different points and then connect those dots together to find the Nyquist plot. Now what happens if I have a particular pole, open loop pole that is, along the j omega axis? So let's say this is the pole for me. At this particular frequency, L of j omega is going to be some numerator divided by some denominator. So when this frequency is the pole of the system, that means the denominator is going to be 0, meaning that L of j omega is going to be infinity. So this particular point, which I have to map to this S-plane, this is going to have a magnitude of infinity, and there is no way for me to plot that. So we have to have a trick in order to avoid situations like that. The trick we do is as follows. Every time we have poles along the j omega axis, we try to skip those by moving around them, as I am showing in this diagram here. So I will start moving up from a negative frequency. When I get to see one pole along the j omega axis, I go around it and I continue the path. I see another one. Let's say here I have an open loop pole at the origin. Again, I skip that and I continue this for every pole that I have along the j omega axis. Then once I've done this, I will continue plotting the Nyquist the way I've done it before. So I will develop the Bode plots, and then for different frequencies I find the magnitude and phase angle, connect them together. Once I do that, however, you will see that your Nyquist plot is not going to be a closed shape, as we have seen before. So in order to close it, for every pole along the j omega axis that I have skipped, I will add a semicircle in the clockwise direction. Now the best way to understand this is to work through an example. Consider this transfer function. You have a system with a transfer function 4 divided by s times s plus 2. The loop gain, L of s, is going to be 4 divided by s times s plus 2. The loop gain has two poles. One is at the origin, one is at -2. Origin belongs to the j omega axis, so this is one pole that is problematic for me. What I would have to do is, when I move along the j omega axis, and notice that I have one pole at the origin, one pole, let's say at -2. Let me use a different color. So when I move along the j omega axis, come here, when I get to 0, instead of moving through it, I will go around it. And then I continue going to a positive frequency. Then what I do is I will do my Bode plot as before. Once I'm done, I will add that semicircle. So let's see how this is going to look like. Let's first start with our step 1, which is rewriting my loop gain in the standard form. This is going to be 4 divided by s, 1, and then s plus 2, I rewrite it as s over 2 plus 1, and then I multiply it 2 here. So my low frequency term is going to be, 2 divided by s. We can write the break frequency table too. It's pretty simple because I only have one break frequency, so the frequency is going to be 2. Type is going to be a pole, which is first order. Where is it located? It's in the left half plane. What is the slope for magnitude? Is going to be minus 20 dB per decade because it's in the left half plane. And the slope for phase angle is going to be minus 45 degree per decade. Let's go ahead and plot the magnitude and phase Bode plots. So let's start with the magnitude. We have 20 log of g. Now, as you recall from a similar example that we did in class, this is a type 1 system. So your low frequency term has an integrator in it, meaning that the starting slope, unlike the previous example, which was a flat line, here the starting slope is going to have a negative slope of minus 20 dB per decade. I do know the slope, but I would have to find one point. If I know one point and the slope, I can say that I know where the line is. So low frequency term, let's say I find its value at one particular frequency, which is less than my break frequency. So let's say frequency of 1. So what is L at J1? It's going to be 4 divided by J1 times 2 plus J1. So magnitude of L at frequency 1 is going to be 4 divided by 1 times square root of 4 plus 1. So it's going to be 4 divided by square root of 5. I don't know exactly how what this value is, but it's going to be greater than 1, meaning that 20 log of it is going to be positive. So let's say at frequency 1 and 2. So let's say as an example, it's somewhere here, right? So you will start with a slope of minus 20 dB per decade. You will continue until you get to frequency 2, which is my break frequency, after which you have another additional minus 20 dB per decade. So let's say you will continue like this. Now I haven't done the calculation, so this particular point, maybe it's positive, maybe it's negative, I'm not sure. But once you do the calculations, you will know for sure whether this particular breakpoint happens in the negative decibel range or positive decibel range. Regardless, that's minus 20 dB per decade, and this is going to be minus 40 dB per decade. How about the phase angle? Let's look at the low frequency term. So low frequency term is 2 divided by s. Angle of low frequency term is the angle of 2 minus angle of s, or j omega. Angle of 2 is 0. Angle of j omega is 90 degrees. So angle of the low frequency term is going to be minus 90 degrees. Okay, and then from somewhere, let's say this is 0.2. more or less, and let's say this is 20. So from 0.2 to 20, I will have a slope of minus 45 degree per decade. So my line starts dropping like this with a slope of minus 45 degree per decade, and once I hit 20, I will have a flat line. Of course, from 0.2 to 20, that's 2 decades, so minus 45 per decade. For 2 decades, that's going to be minus 90, so the ending point is going to be minus 180 degrees. So what I've done so far is I have developed my Bode plots just like before, as if I haven't done anything about this particular pole that was at the origin. Now, this is what I have taken from your handout. Basically, it's a series of frequencies and the magnitudes and phase angles. So what we will do is we will try to find those points and connect them together. So let me use a red color. So let's say starting point is going to be magnitude of 20, phase angle of minus 90 degrees. Then let's say I will have a magnitude of 4 and an angle of minus 100, and then magnitude of 2 and minus 120, then magnitude of 1, let's say, and minus 130. And these are approximate, but you kind of get the idea. And as we go to higher frequencies, we have very, very small magnitudes of like 0.03, 0.01, with angles that are close to minus 180. So it's going to be like somewhere here. So connecting these together, this is a shape that you will see. This is a shape or trajectory for positive frequencies. For negative frequencies, you will have a similar trajectory, except that it's going to be flipped. Now, what difference do you see with respect to other Nyquist plots that we have done in class or you've seen in homework assignments? The big difference here is that, unlike other functions we've seen before, this Nyquist plot is not a closed plot. Why is that? Because I have skipped that particular point, which was my pole along the j omega axis. Because I skipped that pole, essentially my Nyquist plot is not going to be a closed shape anymore. So in order to close it, I'm going to have to add one half circle, one semicircle in the clockwise direction. And typically what you have to do in these cases is that you have to see how you should draw this circle in order to close the shape. In this particular case, it's pretty simple. I would draw the half circle in the clockwise direction, and you will see that it completely closes the circle for me, closes the loop for me. So this is going to be my Nyquist plot. And if you do the analysis, you have z equals n plus p. P is the number of poles that I have in the right half plane, the unstable poles. In this case, that will be 0. Now you might wonder that I have a pole at the origin, and that is considered to be an unstable pole. So why do I not consider it here? Well, that's because when I chose the trajectory along which I go from very large negative frequencies to very large positive frequencies, I skipped that pole by moving around it. Because of that, I consider that pole not to be among the unstable poles of the open loop, so I don't count it as one of those unstable poles. So I have 0 here, and then minus 1 is most likely somewhere here, so I'm not encircling minus 1, meaning that my closed loop system is going to be stable. Now if you have more number of poles along the j omega axis, the analysis is going to be the same, except that for every pole you're going to have to draw one half circle in the clockwise direction. Let's consider this example. Your loop gain is 50 times s plus 4 divided by s squared times s plus 1 times s plus 3. Here you can see that I have 2 poles along the j omega axis, both of which happen to be exactly at the origin. So what you will do is you will plot the Bode plot as we have done before, and you will end up with this shape. And let me actually draw this a little bit more accurately so you see how you would have to add the circles. If you actually plot the Bode plot carefully and find the points and connect them together, your Nyquist plot is going to look something like this. Right? Again, as you can see, it's not a closed shape. So what I would have to do is I would have to add 2 half circles, because now I have 2 poles along the j omega axis, both in the clockwise direction. This is where you have to play a little bit with the plot to see how it would make sense to add those circles. In this particular case, as you can see here, I kind of end up at this point. So I will have one, let me connect this exactly here, 1 half circle in the clockwise direction, and it kind of has to connect to this particular path because of the direction. So this is sort of in the clockwise direction, and it has to continue the clockwise direction, and then you're going to have another half circle in the clockwise direction, which will then be connected to this particular point. And this will be your Nyquist plot. Now let's do the analysis for this guy. So z equals n plus p. Again, you see here that despite the fact that I have 2 poles at the origin, because I have skipped those, so essentially if you look at the poles, I have 2 poles, open loop poles at the origin, 1 at -1, 1 at -3, but what I did was I moved around them. So I came here and then I skipped them and continued my trajectory. Because of that, I do not consider these 2 poles among the unstable poles. So I would say I have no poles in the right half plane. And how many times do I encircle -1 in clockwise direction? The best way to figure that out is to draw a line in really any direction and see at how many locations it crosses a Nyquist plot. It crosses it in 2 locations, and both locations it would be in a clockwise direction. So that would be at 2. And z will be 2, meaning that if you close the loop with this particular system, you will have 2 unstable poles, 2 closed loop poles that are in the right half plane. So this brings us to the end of our discussion on Nyquist stability analysis. I do encourage you to do a few examples, either from your handout or from homework assignments, just so it becomes a little bit more comfortable how you do the analysis and how you draw the Nyquist plot. When we continue our discussion next week, we will talk about how to take this concept of Nyquist stability one step further and assess the margin of stability of systems, which is defined in terms of gain margin and phase margin.